Hey everyone, my name is Omar, and today I'll be telling you about random Solomon codes and why they achieve this kind of capacity over linear-sized fields. This is joint work with Menke Goswami and Ray Lee. So let me first tell you what read Solomon codes are. So read Solomon code takes a message M of length k, interprets its symbols as elements from a finite field, then defines a polynomial f whose coefficients come from the message M, and evaluates this polynomial across n different points. And that defines the encoding of the message M. Now, there's a well-known fact that if you take any two distinct code words, then you define at least n minus k plus 1 positions, and by the distinctive bound, this is information theoretically the best we can hope for. Now, this fact is equivalent to just saying that any k distinct evaluation points of the polynomial f uniquely determine the polynomial and therefore the message m. And this last fact follows from simply Lagrange interpolation, which if you know over the real numbers, then it works as is over the finite fields with hardly any modifications. So this is a classical ensemble of error correcting codes that's been known since like the 60s. And in this talk, we're interested in seeing if it's list code, its list decoding capabilities. So let me tell you what list decoding is. So list decoding says that if you take in a Hamming ball of radius p and look at the code words in the Hamming ball, then there's almost L code words in it. And here's the formal definition of it, but let me give you a pictorial picture of what that means. So your code word, think of your code words as points in space. And take any Hamming wall of radius Pn, where P is some fraction between 0 and 1, and look at the number of codes inside the Hamming ball. Then the code is P, L list decodable if there's at most L codes in the Hamming ball. Now, here we're going to think about L as being a fixed constant, let's say 1, 2, and 3. And in that case, we're wondering how big can P be if we fix L. Now, it follows from a simple pigeonhole argument that for a fixed L, the largest that P can be is L divided by L plus 1 times 1 minus R. Now here, R is the rate of the code, which is simply the message length divided by the code word length. In other words, it's K divided by N. And when you think about L as like being a large constant, then if the code achieves this bound, then we say that achieves the list decoding capacity. In other words, a code achieves the list decoding capacity if it is 1 minus R minus epsilon, comma, O of 1 list decodable for small enough epsilon. Then and if this is the bound that you get by just picking L to be a large enough constant in the claim above. Now we know this is not a random bound. We know the random codes of a large enough alphabet actually achieve the list decoding capacity. And this talk we're interested in seeing seeing read Solomon codes achieving the list decoding capacity too. So so what do we know about this code of read Solomon codes? First, we know there's the classical result of Goswami-Sejan that says that read Solomon codes can be efficiently list decoded up to the radius 1 minus squared R minus epsilon with constant list size. Now, where does this number come from? It follows from the Johnson bound, which is a standard list decoding result that you can get from just knowing the distance of the code. So by relative distance, I mean the minimum fraction of coordinates that two codes can differ on. But we're hoping that we can go beyond the Johnson bound for read Solomon codes. So the question is, can arbitrary read Solomon codes achieve this kind of capacity? Now, there is some obstructions that you should take with a grain of salt that says that you can't really hope for that to happen. That's only for arbitrary read Solomon codes. It's possible that you can cherry pick your evaluation points more carefully and avoid these challenges. So our motivating question is, are there any read Solomon codes that are commutatorily decodable up to capacity? So here are a few motivating reasons why we care about this question. So we know some explicit codes that achieve the list decoding capacity with efficient algorithms. But these codes turn out to be variants of read Solomon codes, such as fold read Solomon codes and multiplicity codes. So it'd be nice to know if the original code, which was the read Solomon code, was commutatorily decodable up to capacity from the beginning. The other reason is that this could be read Solomon code had numerous applications in complexity theory and pseudo randomness. So the list code read Solomon code is a classical tool in complexity theory and pseudo randomness. The reason is that read Solomon codes are the most typical class of codes that you see that also achieve the singleton bound. So they're the simplest class of codes out there. And in this talk, we're interested in seeing if random means element codes achieve this decoding capacity combinatorially. So there's been a lot of work trying to study random means element codes, and this culminated in the breakthrough of Brackensee, Gopi, and Markham, in which they showed that random means element codes achieve this decoding capacity for exponential fields. Now, this breakthrough work has wonderful connections to higher order MDS codes and GMMDS theorem, which I won't get into, which I unfortunately can't get into in this talk due to time constraints. But I should also mention that the result also achieves the generalized singleton bound, which is a more fine-grained result than just achieving this kind of capacity. And the generalized singleton bound is what is the following. So we say a code achieves the Lth generalized singleton bound if it's L over L plus 1 times 1 minus R comma L, this decodable. So that's the bound. This is the largest radius that you can get for a fixed L that we stated before in the previous claim. So in fact, they show that random means element codes also achieve the Lth generalized singleton bound for any fixed L, at least 2. So here's a result for in a more here's a more detailed statement of the result for generalized singleton bound. Now the thing is that the field size that they have is exponential, so it'd be nice if we can bring this down smaller. Now unfortunately, there's a follow-up result by Brackensee, and Gopi. They show that if you take any linear code that uses the first and second generalized singleton bound, which is the case for random means element codes, then the field size must be exponential. So that's an obstruction to exactly attaining the generalized singleton bound. But the catch is in exactly attaining the generalized singleton bound. So if you look at the definition of achieving list decoding capacity, we're fine with getting away with the epsilon gap to the generalized singleton bound. So if you incorporate this epsilon gap, what happens? So by a result of Guo and Zhang, they show that if you're epsilon away from the generalized singleton bound, then actually randomly element codes can achieve it with high probability for a quadratic field size. So in other words, Q's randomly element codes achieve the generalized singleton bound for quadratic field sizes. Now resettlement codes always have a linear field size, so it's almost close to getting the optimal field size. So the actual question is if we can bring the field size from quadratic to linear. And in this work, we optimize their proof down to the linear field size, which is the most optimal field size that you can hope for. So here's our main result in the most formal sense. So for a large enough field size Q that's still linear in N, a random means element code is upside away from the Lth generalized singleton bound with high probability. Now by using the same proof framework that we have, we also show that random linear codes over large but constant field size are also epsilon away from the Lth generalized singleton bound with high probability. I won't get into this result, but the proof follows almost seamlessly from main result. But the main takeaway here is that random means element codes achieve this decoding capacity with optimal alphabet size, which is great. So we know that random means element codes can combinatorially achieve this decoding capacity, but there's still some obvious follow-up questions, which is are there explicit Reed element codes or efficient algorithms for this decoding Reed element codes up to capacity? But as a first step, we know that there are a lot of good Reed element codes out there. So since we posted this work in like last year, around April, there's been a lot of wonderful work that build on this this framework that started with the work of Brackensee, Gopi, Makam, then Guo Zhang, and then our work. And I just wanted to quickly mention them. So there's this wonderful work that's also in this year's stock by Brackensee, Dar, Gopi, and Zhang that show that random algebraic geometric codes are also epsilon away from the generalized singleton bound for constant field sizes. So it's a wonderful work, and you should check it out. There's also been a couple of other works that use this proof framework for random faulty Reed element codes and for random gap dueling codes. Now, gap dueling codes is a code for a rank metric, which is a bit of a different setting. And with that, I'm going to give a proof sketch of our main result. So let me first begin by telling you roughly how the proof of Brackensy, Gopi, and Markham goes, since we heavily rely on that in our proof. Okay. So say you have a PCOM list decodable code. Now a code is PCOM list decodable if and only if there is no bad PCOM list decoding configuration in it. Um, What do I mean by balanced configuration? I just mean the Hamming ball radius Pn that has L+1 code words. So if you don't have any Hamming ball with a lot of codes in it, then then the code is immediately list decodable, and that just follows from the definitions. And here's the main challenge in this problem, which is that there's a lot of bad list configurations, in particular q to the n times L+1 of them, roughly, give or take. There's very little randomness in random read Solomon codes. In particular, there's only almost q to the n, like possible read Solomon codes. So there's a lot of bad events that are much more than the amount of randomness that you have. That's what makes the problem quite challenging. And the key, like the key in this problem is to try to exploit the structure of read Solomon codes, in particular some of their symmetries. And the question is, how do we do that? So because the number of bad decimal configurations depends on Q. It'd be nice if we can get if we can categorize them in a different way. And one way you can do that is based on their agreement patterns. So if you look at the way that these codes CI agree with Y, in total there's only almost like 2 to the NL agreement patterns between them. Let me tell you what I mean by agreement pattern more formally. So here's your coded Y at the bottom, and say like 4 coders are in its Hamming ball. So if you color the entries of Y in different colors, then because these codes CI are in the Hamming ball of Y, it means that they agree with Y on a lot of places. So it means that there's a lot of colors that match in the CIs that match the Y. And because read Solomon codes are linear codes, what we could do is we can try to linearly encode these agreements between the CIs. Yeah. So the key idea in the proof framework that we use, and both in Golang and in Brackensy, Gopi, and Makam, is to linearly encode all these linear constraints that are imposed on the CIs just from their agreement patterns with Y. Okay, and we want to do it in the most minimal sense. Okay. So in other words, we want to pick the least amount of agreements that can least amount of constraints that capture all the agreements between the CIs. And the idea is to show that for every agreement pattern that comes from a bad disciplinary configuration, the linear constraints, the matrix that these linear constraints form, turns out has to be full rank, and therefore there can never be any any configuration that satisfies this agreement pattern for every agreement pattern that comes from a listed configuration. So because of that, there's no bad listed configuration in the code C, and therefore it is list decodable. That's how the proof initially goes. So how do we do this in the algebraic encoding? So let me give a high level how that goes. So here's the agreement pattern that we had before, and what we're going to do is define this like so. First, let me say what the generating matrix of the read Solomon code is. So fix it. Let G be the generating matrix of the read Solomon code, which basically has n rows, each of length k. Now each row here is just the powers of each evaluation. So it's 1, AI, AI squared all the way to AI to the k minus 1. And because the CI is a code words, you can write each code word CI as the encoding of some message fi, okay, of length k. Now we're going to define this giant matrix, which takes all the agreements between the CIs. Now, how do we do this? This is a pretty big matrix, so let me go through it a bit slowly. So, and you go to each coordinate and you take all the linear constraints imposed by it. So if you go, so in the first coordinate, it's purple. There really isn't any agreements between the CIs, so we just ignore it. But if you go to the red one, there's agreement between C2 and C3. So we encode that as one constraint. Okay. Now in the third coordinate, there's agreements between C1, C2, C2 and C3, and then C1 and C3. That's 3 agreements, but to encode it in the least number of ways, we just encode the agreement between C1 and C2, and then the agreement between C1 and C3, and we just continue doing this procedure. on and on. Okay. So because of the way we define this matrix, if we look at not the code word CI, but the messages that they encode, they will be in the kernel of this matrix. Now, there's a small nuance here that this matrix is not always full rank for a very obvious reason. It's because if you repeat the messages L+1 times, that's also going to be in the kernel always. As for an obvious reason, is that if you have any bad discrete configuration, then if you shift it by any code word in your code, that will also be a bad discrete configuration. So we also want to account for that symmetry in our matrix to make sure that it's full rank. So let's just try to get rid of this small nuance. And one way you can do that is just to delete the first block of columns. So if we delete the first block of columns, then there's no obvious vectors in the kernel of this matrix. Yeah, and that defines this so-called reduced intersection matrix, or in short, RIM. Yeah. Here, if H nodes are agreement pattern, then for every agreement pattern, there's a RIM matrix associated to it. Okay. Now and that's what the first key definition that we have. So now our goal is to here's a ring matrix, and our goal is to show that every ring matrix is full rank. So why do we want to do that? Is because if we start with a balanced configuration with agreements from H, then that says that the ring matrix is not a full rank matrix. So we want to look at the probability that the ring matrix is not full rank. So think of the evaluations as form of variables. And there's this result of from Brackensee, Gopi, and Makam. This is that if you take any minimal agreement pattern, we're not going to worry about minimality because that's a technical issue. So just think of any agreement pattern coming from a bad discrete configuration. Then it turns out that this rim matrix is symbolically full rank. So what does that mean? It means that if you think of the evaluations as form of variables, then this rim matrix is not is full rank over the field that these AIs generate on that field. So that's a very mouthful. So what am I trying to say in short? It means that if you take the rim matrix, there's an LK by LK submatrix in it that has a small chance, that has a good chance of being not full rank. And the key observation is that the degree of this determinant is actually small. So in other words, by the Schwarz-Zipper lemma, the rim matrix has a small chance of being not full rank. So in other words, there's a good chance that the rim matrix is full rank. In other words, the rim matrix has a chance of at most LK over Q of not being full rank. And since there are at most 2 to the n times L+2 possible agreement patterns, and if you pick a large enough Q exponential on n, then and unibounding over all possible configurations H, we are done. Okay, so that's in short what the proof of Brackensee, Gopi, and Markram goes. And now, we're going to give a high-level view of the Guo and Zhang proof based on the proof framework of BGM. Okay. So the Guo-Zhang proof follows basically the same framework that we just described, but they have to incorporate the epsilon gap to the general singleton bound. So how do you do that? So the key observation is that if you have any bad list configuration with the epsilon gap incorporated, and if you remove epsilon n coordinates in it, it is still a bad list configuration. So using that fact, if you take any rim matrix, you can also amplify the probability that it's not full rank by a lot. How do you do this? So you consider the matrix M1 that you get from the main result of the BGM, and you're going to produce several matrices, square matrices inside of it. So here's a matrix M1. What you're gonna do is delete this color, the purple color from it, and therefore you still get a balanced configuration. But if you repeat this several times, you can get a bunch of matrices M1, M2, M3. Where each previous matrix has a new variable that doesn't show up in the previous ones. So formally, I'm just saying that if you use a BGM theorem a few times, then you can get not only one matrix that is symbolically full rank, but epsilon n of them. Okay, and you have the same observation that the degree of the determinant of each matrix is at most LK. So you can apply Schwarz-Zipper again, and therefore amplify the probability to power epsilon n. I'm skipping a lot of high level details, but the high level idea is that each matrix Mi has a variable that doesn't show up in the later one. So you can iteratively apply Schwarzschild from the end to the beginning, step by step. And then you apply the same union bound, only now you have to account for the deletion sequences that you've done before. So you have an n to the epsilon n possible deletion sequences that you have to account for. And if you do this union bound, then you get this q. Then you need that q is at least n squared, give or take, and that finishes the proof of Gorjang. Now the reason why I get n squared is because there's a lot of deletion sequences that you get. Now, if there's a way you can reduce this number of deletion sequences, then you can bring the size, like the field size q down to a much smaller number. And the main contribution of our work is actually getting this sequence, this number of possible sequences down. Okay. So our key observations are actually you can reduce the number of sequences from n to the epsilon n down to like 2 to the O of n. And because of that, if you apply the union bound procedure as we did before in the previous slide, then we conclude our main result. So how do we get a much smaller deletion sequences? So consider any agreement pattern that we have on the right, and we categorize the colors based on their types. So we just the way they agree in each coordinate. Okay, and you classify, you get a very few number of types, a constant number, and therefore each type class has a lot of colors in it. And our first step is, we delete like some fraction of colors from each type. And the reason we do that is because if you look at all the types that have survived after deleting this amount, then each one has actually omega n colors in storage. So if you do this, so the second step is first order the n colors based on their type. And we did the same thing as Gorjang in the previous slide, but now we're going to do something a little different. Is that first we're going to delete in like this sequence that we define in step 2 in order. Otherwise, if we end up to the end, we just restart. And whenever we delete a color, and this is the key observation, like on our proof, whenever we delete a color, we're going to have omega n colors in storage for it. So that if we remove this color and replace it with another color of the same type, this matrix is still symbolically full rank. Okay, so we can keep replacing each color with something in storage of the same type, and that matrix will always still be symbolically full rank. That's ensure what our key, like the key observation in our work is. Okay, so because of the way we do this, we actually get a deletion sequence that has a most a constant number of peaks. So the deletion sequences that we get are very structured. So if that was a mouthful, so here's what the deletion sequences look like in our work. Deletion sequences go up to a high peak, and then it goes down, and then it starts going up again and down. And if you look at this graph, then really there's only almost a constant number of peaks. And because of that, if you do some combinatorics, you just get that the number of sequences you can get that look like that is almost like 2 to the O of n. And so therefore that establishes our key observation, and therefore the main result of our work. And that's in short how the proof how our proof goes. It really builds on the previous works of Guo and Zhang and the work of Bakasi, Gopi, and Makam. And that finishes it. So thank you.